Hold a glass marble between two fingers. It is small enough to lose under a sofa, ordinary enough to ignore, and heavy enough to feel real. Now give it a speed that nature will not let any massive object reach exactly, 99.9% of the speed of light. That marble is no longer an everyday object. Its motion carries roughly the energy of a multi-megaton explosion. Now stop the rotation of Earth. Remove the sun without warning. Open a human body to vacuum. Fall toward a black hole. Each request contains an impossibility, an undefined mechanism, or a journey far beyond our technology. But the moment after the impossible premise can still teach us something real. Momentum remains momentum. Signals still have a speed limit. Pressure, radiation, gravity, and spacetime still follow rules. That is the method of this documentary. We will not pretend that an impossible event has one perfectly exact outcome. When the premise leaves out an essential detail, we will say so. When a number can be calculated, we will calculate it. When a popular image is wrong, we will replace it with the less familiar physics underneath. These are not predictions and they are not disaster instructions. They are stress tests for intuition. Everyday life trains us at low speeds, mild pressures, weak gravity, and temperatures that biology can survive. At the limits, that training fails. The universe does not become irrational. Our shortcuts do. 10 scenarios will take us from a 5-gram object to the largest horizon we can observe. The scale changes by more than 40 orders of magnitude, but the question stays the same. What would actually happen, and how much of the answer can physics honestly defend? We will use 3 different kinds of answer. Some results follow directly from an equation, such as relativistic kinetic energy. Some are qualitative consequences supported by experiments and observations, such as hypoxia in vacuum. Others require a numerical model because geometry and material behavior evolve together, such as an asteroid-generated wave. Treating all 3 as equally precise would create confidence that the evidence does not deserve. Chapter 1. The relativistic marble. Our marble has a rest mass of 5 grams. Its speed is 0.999 times c, where c is exactly 299,792,458 meters per second. The premise requires an impossible launcher and an impossible amount of control. We will simply place the marble in empty space, already moving toward Earth, and ask what its motion means. At ordinary speeds, kinetic energy is 1/2 mv squared. That equation serves cars, aircraft, and most spacecraft extremely well. It does not survive unchanged near the speed of light. Special relativity uses a factor called gamma. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. At low speed, gamma is almost 1. At 99.9% of c, gamma is about 22.4. The kinetic energy is gamma minus 1, multiplied by mc squared. Put in a mass of 0.005 kilograms and the result is about 9.6 petajoules. Using the conventional energy equivalent of TNT, that is roughly 2.3 megatons. The marble has not gained a magical explosive chemical. Its enormous energy is the energy required to establish its motion relative to Earth. This distinction matters because people sometimes explain relativity by saying that the marble's mass becomes larger. Modern treatments usually keep its invariant mass at 5 grams and describe the growth of its energy and momentum instead. The closer a massive object approaches c, the more energy is required for each additional increase in speed. Reaching c would require an unbounded amount of energy. The marble can approach the limit, but it cannot become light. If Earth had no atmosphere, the collision would still be extreme, but that is not our planet. Long before the marble approaches the surface, it encounters atoms and molecules in the upper atmosphere. At its speed, individual collisions are high-energy particle interactions. The glass structure cannot remain an intact, polished sphere. Its atoms interact, fragment, ionize, and join a growing shower of secondary particles. Cosmic rays demonstrate the basic process on a much smaller scale. A sufficiently energetic incoming particle strikes a nucleus in the atmosphere and creates new particles. Those products collide again. The result is an extensive air shower, a branching cascade that distributes energy through a widening volume of air. Detectors on the ground can reconstruct an event that began far above them from the particles that survived the journey. Our thought experiment marble is macroscopic, so translating a cosmic ray shower model directly into one precise burst altitude or damage radius would be dishonest. The object has a particular composition and shape. The atmosphere changes density with altitude. The path may be vertical or oblique. At these energies, detailed results require a simulation that resolves particle physics, radiation transport, and atmospheric hydrodynamics together. What we can defend is the central conclusion. The marble does not make a normal glass-on-rock impact. Most of the story becomes an atmospheric energy deposition event. There would be intense ionization, radiation, heating, and a powerful disturbance in the air. The exact partition among light, particles, heat, and mechanical blast is a modeling question, not a number hidden inside the simple kinetic energy equation. This is why a cinematic crater can be scientifically misleading. It tells the viewer that the marble stayed a marble until the final frame. In reality, the first meaningful target is the atmosphere. The atmosphere is not an empty visual layer. At relativistic speed, even its thin upper edge is material enough to end the identity of the object. The 5-gram marble exposes two limits at once. The first is c, the local speed limit for matter and information. The second is the limit of a back-of-the-envelope calculation. Relativity gives us the energy with confidence. It does not, by itself, give us a city map of the consequences. A responsible answer stops where the equations stop and identifies the simulation that would have to continue. Energy and momentum also answer different questions. Energy helps describe how much physical change is available. Momentum helps describe direction and the difficulty of redirecting motion. Two events can share an energy scale while depositing it over different volumes and times, producing very different effects. Comparing the marble's energy with an explosive is useful for scale, but it does not make the atmospheric event physically identical to a nuclear detonation. Keep the idea of retained motion. We are about to apply it not to a marble arriving from space, but to everything already riding on a rotating world. Chapter 2. Earth stops rotating. Earth turns once relative to the distant stars in about 23 hours and 56 minutes. At the equator, that rotation carries the surface eastward at approximately 465 meters per second, or about 1,670 kilometers per hour. At higher latitudes, the eastward speed is smaller. At the geographic poles, it falls to essentially zero. We do not feel this motion because the ground, atmosphere, oceans, buildings, and our bodies share it. Constant velocity is not something an accelerometer notices. A passenger in a smooth aircraft can pour water almost as if the cabin were stationary. What the body notices is acceleration, a change in velocity or direction. Now impose the impossible premise. The solid Earth stops rotating in an instant, but we have not specified a force that also stops the atmosphere, the oceans, or loose objects. That missing mechanism is crucial. Conservation of angular momentum says the rotation cannot simply disappear. Any real process capable of removing it would exchange enormous momentum and energy with something else. Our scenario hides that process, so we cannot calculate the complete event from first principles. We can still examine the immediate relative motion. Near the equator, material that is not forced to stop retains an eastward velocity close to 465 meters per second. That is faster than the local speed of sound in ordinary surface air. The ground beneath it is now stationary in our chosen frame. Near the poles, the initial difference is much smaller. Between those limits, it scales with latitude. This means there is no single global launch speed. A diagram that throws every city eastward at the equatorial value is wrong. So is the claim that the retained motion sends everything into space. 465 meters per second is far below Earth's escape speed. Gravity remains. Objects in air would move violently relative to the stopped surface, but they would remain gravitationally bound to the planet. The atmosphere is a fluid with depth, temperature, and friction. Its motion would not become one neat, uniform wind for long. It would interact with mountains, buildings, the ocean surface, and itself. Shock waves, turbulence, compression, and heating would redistribute momentum. The severity would depend strongly on latitude and terrain. We can say that the differential motion would be catastrophic across much of the planet without inventing one universal wind map. The oceans retain angular momentum too. Their response would not be a single clean wall of water with a fixed height. Basins have different shapes and depths. Continents redirect flow. Coastlines focus or disperse waves. Enormous transients and flooding are reasonable consequences, but a precise global tsunami requires a model and a definition of how the solid Earth was stopped. Rotation also helps shape the planet. Earth is slightly wider around the equator than from pole to pole. If rotation remained absent, the long-term equilibrium shape would be more spherical. Rock and water would adjust toward that new distribution under gravity. That readjustment would take time and involve the mechanical behavior of the mantle and crust. It is not an instantaneous animation in which the equatorial bulge snaps flat. The calendar would become strange as well. Stopping Earth's spin is not the same as locking one face permanently toward the Sun. If Earth continued to orbit while keeping one orientation relative to distant space, the direction facing the Sun would change during the year. A solar day would last roughly one orbital year, a long daylight season followed by a long night. The exact climate would depend on atmosphere, oceans, geography, and how much of them survived the initial event. Rotation influences weather through the Coriolis effect, but it does not create all weather by itself. Without daily rotation, the familiar organization of winds, storms, and ocean circulation would be transformed. Large temperature contrasts would still drive motion. The resulting climate would be alien, but claims that one side must permanently boil while the other permanently freezes belong to a different scenario, tidal locking. Earth's magnetic field is generated by motion in its electrically conducting liquid outer core. Rotation matters to the organization of that geodynamo, but it is not honest to assign an immediate shut-off time from this thought experiment. The core has its own inertia and convection. The same undefined torque that stops the crust may or may not act on the deep interior. This is another place where the missing mechanism controls the answer. There is an enormous accounting problem hidden in the word stop. A rotating planet carries kinetic energy. If an external interaction removes its angular momentum, energy and momentum must be transferred, dissipated, or stored somewhere. Different stopping mechanisms could heat the planet, deform it, eject material, or transfer motion to another body. Our simplified scenario deliberately ignores that first cause, which means the retained motion consequences are the minimum story, not a complete energy budget. The lesson is not simply that spinning is dangerous. It is that shared motion feels like rest until different parts of a system stop sharing it. The surface speed is measurable. The latitude dependence is measurable. The total catastrophe is underdetermined because the impossible stopping force has never been defined. Our next scenario removes something even more fundamental. This time Earth keeps its motion, but the mass that bends its orbit disappears. Chapter 3. The Vanishing Sun. The Sun cannot vanish. Conservation of mass energy does not allow a star to be deleted from the universe without an enormous physical process and consequences of its own. We will suspend that rule for one moment. At a chosen instant, the Sun is gone, and nothing replaces it. Earth would not know immediately. The average Earth-Sun distance is about 1 astronomical unit, and light takes roughly 8 minutes and 20 seconds to cross it. We always see the Sun as it was more than 8 minutes ago. General relativity also forbids a gravitational change from propagating instantaneously. Information about the missing mass travels at sea. For that interval, local observations on Earth continue as before. Sunlight already in flight arrives. The space-time geometry at Earth still reflects the earlier state. Earth follows essentially the same orbit it was already following. There is no advanced shadow and no early gravitational twitch announcing what happened. When the final sunlight reaches Earth, the optical change is immediate on human timescales. Daylight ends. At approximately the same time, the change in the Sun's gravitational influence reaches us. Earth no longer follows its former curved path around the Sun. Its existing orbital velocity does not disappear. It continues approximately along the tangent to the orbit it had at that moment. That speed is close to 30 kilometers per second. Earth becomes a rogue planet moving through the galaxy. It does not shoot radially away from the old solar position as if repelled. It follows the direction its orbital motion already gave it, modified over longer times by the gravity of other bodies and the galaxy. The phrase, "everything goes dark at once," needs care. The moon and planets shine mainly by reflected sunlight, but the timing of what we see depends on geometry and light travel paths. The last light reaching another world and then reflecting toward Earth does not have the same route as direct sunlight. Different objects would fade according to their positions. The solar system would not perform one perfectly synchronized blackout. At Earth's surface, photosynthesis stops as soon as usable sunlight is gone. Plants and food webs do not all fail on one clock. Stored chemical energy, seeds, migration, predation, artificial agriculture, and human infrastructure create different delays. But the dominant external energy source for the biosphere has ended, so the broad direction is unavoidable. Cooling is also not an instantaneous freeze. The oceans store far more heat than the atmosphere. Water circulates. Ice that forms at the surface can insulate liquid below. The crust and mantle continue to release internal heat produced by planetary formation and radioactive decay. Any exact statement such as, "the average temperature reaches this value after exactly 1 year," depends on a climate model and its assumptions. What can survive without sunlight? Some ecosystems already live without direct solar energy. Microbes and animals around hydrothermal vents rely on chemical reactions supported by material from Earth's interior. Subsurface microorganisms inhabit rock and water far from daylight. Their future would depend on local energy, nutrients, pressure, and the changing ocean above them, but their existence proves that sunlight is not the only energy pathway available to life. Human survival would be an engineering question under rapidly worsening conditions, not a simple countdown. Shelters could use nuclear or geothermal energy. Food could be produced under artificial light for some population. Heat could be managed locally. None of that replaces a planetary climate system powered continuously by a star. Infrastructure failure, resource limits, and ecological collapse would matter as much as the final equilibrium temperature. Over long times, surface oceans would freeze from the top downward. The atmosphere would change as gases condensed at sufficiently low temperatures. The thickness of ice and the persistence of liquid reservoirs would depend on geothermal flow, salinity, pressure, and time. The planet would remain internally active long after its familiar surface was gone. The disappearance also separates information from influence. We sometimes imagine that gravity is a permanent line stretching from Sun to Earth, ready to snap instantly. General relativity instead describes a local geometry that evolves causally. Earth responds to the gravitational field in its neighborhood. A change at the Sun affects that neighborhood only after the change can propagate across the distance. The 8-minute delay is therefore not the gravity arriving late behind the light, both changes respect the same causal structure. This impossible disappearance reveals a real feature of the universe: causality has a finite speed. Gravity does not provide privileged instant communication. For 8 minutes, Earth is connected to a Sun that no longer exists in the premise because every local interaction is built from information still traveling toward us. The next limit is much closer to the human body. Remove not a star, but the thin layer of pressure surrounding us, and familiar cinematic intuition fails again. Chapter 4. The Human Body in Vacuum. Space does not pull objects outward like an invisible suction machine. Vacuum is the absence of surrounding gas pressure. On Earth, the atmosphere presses on every surface and our internal pressures exist in balance with it. Remove the atmosphere quickly, and that balance changes faster than the body can adapt. Science fiction often shows a person exploding or freezing instantly. Neither image describes the first moments well. Skin and connective tissue can contain considerable swelling. Heat cannot leave the whole body instantly because vacuum eliminates convection, and thermal radiation is not an instant deep freeze. The urgent problems are decompression and the loss of usable oxygen. Gas already inside the lungs expands as ambient pressure falls. A rapid pressure change can injure delicate lung tissue. This is why vacuum exposure cannot be reduced to a clever survival trick. The rate of decompression, lung volume, suit or chamber conditions, and speed of repressurization all matter. A documentary should describe the mechanism without turning an accident into instructions. At sufficiently low pressure, water can change phase at body temperature. The name for vapor formation in body fluids under low pressure is ebullition. Moisture on exposed surfaces can begin to boil without being hot. Soft tissues may swell. This still does not mean the blood throughout the circulation instantly boils away. Blood vessels and tissues maintain local pressure, and the body remains a mechanically connected system. NASA's historical discussion of rapid decompression includes a chamber accident in which a test subject remained conscious for about 14 seconds. He later remembered the moisture on his tongue beginning to boil before awareness ended. Repressurization began quickly, and he recovered. That event is valuable evidence that Hollywood's instant explosion is wrong. It is not a universal stopwatch for every body or every decompression. Consciousness depends on a continuous supply of oxygenated blood to the brain. Once no breathable oxygen is available, the useful interval is short. Exertion, prior breathing gas, pressure history, health, and the exact exposure change it. A range observed in experiments or one accident should never be presented as permission to wait that long. Other hazards exist. Gas bubbles can disrupt circulation. Low pressure can damage ears and lungs. Direct solar ultraviolet radiation can injure exposed tissue. In sunlight, one side of an object may heat while a shaded side cools. None of these requires the body to become an ice statue in seconds. The difference between vacuum and low-pressure atmosphere also matters. At very high altitude, there may still be gas present, but too little partial pressure of oxygen to support consciousness. At still lower pressure, water's boiling point falls below body temperature. Engineers therefore design life support systems around both oxygen delivery and pressure, not oxygen percentage alone. A spacesuit is not simply warm clothing. It is a mobile pressure vessel with oxygen, carbon dioxide removal, thermal control, communication, and layers that manage radiation and micrometeoroid risk. The suit lets a human carry a tiny artificial environment into a place that supplies none of the conditions biology expects. Engineers describe pressure in absolute terms because the difference matters. Sea level pressure is roughly 1 atmosphere, while a suit may operate at a lower pressure with a controlled breathing mixture. Lower pressure can improve mobility but changes decompression planning and fire risk. Those trade-offs show why one statement such as, "there is oxygen," cannot establish safety. A habitable environment is a coordinated system of total pressure, oxygen partial pressure, temperature, humidity, and removal of waste gases. The most honest summary is quieter than the movie version. Vacuum does not need to tear a body apart. It only has to remove pressure and oxygen. The machinery of consciousness then loses the environment that makes it work. Survival in documented accidents depended on the exposure being brief and pressure being restored, but no precise safe duration follows from those cases. Pressure can be absent, as in space. It can also arrive violently through a material that normally feels gentle. That brings us to water, where the dangerous myth is almost the reverse: the liquid is said to become a solid. Chapter 5. High-speed water impact. 200 km per hour is 55.6 meters per second. Consider an object or body meeting a water surface at that speed. The water does not change phase. Its molecules do not lock into a crystal lattice. It remains a liquid before, during, and after the impact. The danger comes from momentum transfer over a short time and distance. To enter the water, an object must accelerate some surrounding water out of its path. That moving water behaves like additional effective mass coupled to the object. Engineers call this idea added mass or virtual mass. The exact amount depends on shape, orientation, depth, and the evolving cavity around the object. At low speed, water has time to flow around a swimmer or boat hull. At high speed, the flow must accelerate extremely rapidly. Pressure becomes large, the free surface deforms, spray and cavities form, and the object decelerates. The fact that liquid can flow does not guarantee that it can move out of the way gently within a few milliseconds. This is hydrodynamic loading, not surface tension turning the ocean into pavement. Surface tension matters for droplets, insects, and small-scale interfaces. It is not the main explanation for the trauma of a full-sized high-speed impact. Density, geometry, velocity, and the time history of deceleration dominate the event. One simple equation helps without pretending to solve the whole collision. Acceleration is change in velocity divided by change in time. If a velocity near 55.6 meters per second is removed in a very short interval, the magnitude of deceleration is large. But the interval cannot be guessed from speed alone. Water depth, waves, aeration, body shape, rotation, and structural deformation affect it. Some hydrodynamic force terms scale with velocity squared. That makes speed especially important. A modest increase can produce a much larger change in loading. Yet a velocity squared relationship inside a model is not a universal prediction of human g-force. Anatomy is not a rigid test shape, and different parts of a body can decelerate differently. Historical reports examined rare survivors of high-velocity falls into water. Associations between entry geometry and outcomes appeared in those cases. They do not establish a technique or a safe threshold. Survivor reports are selected from unusual events and cannot tell us that repeating a posture will repeat an outcome. The proper use of the evidence is to understand variables, not to offer advice. Trauma can arise because external surfaces and internal organs do not share exactly the same stopping history. Tissues stretch, vessels load, and organs move relative to supporting structures. Describing those mechanisms is enough. Graphic certainty about a specific injury at a chosen speed would require a biomechanical model and individual anatomy that this thought experiment does not provide. NASA treats water landing as an engineering problem rather than assuming the ocean is soft. Capsule shape, attitude, vertical and horizontal speed, seat design, restraint systems, and crew posture are evaluated together. Simulations and instrumented tests estimate acceleration histories so the vehicle can keep loads within designed limits. The water flow itself can change regime during contact. A cavity may open behind an entering object. Air can become entrained. Local pressure can fall enough for vapor cavities to form and collapse, a process related to cavitation. Flexible structures bend and absorb energy. These effects can change the force curve from 1 millisecond to the next, which is why a single average deceleration cannot describe the peak loads on every component or tissue. That is also why a controlled spacecraft splashdown does not validate uncontrolled high-speed entry. The capsule has a broad engineering system managing energy before and during contact, atmospheric drag, parachutes, structure, seats, and the water itself. The final water interaction is only one part of the chain. The myth says water becomes concrete. The physics says something more useful: water remains water, but moving it rapidly requires force. A liquid can transmit destructive loads without becoming a solid. Once we stop asking which material it resembles, we can study the actual flow. Our next threat is harder to see. It crosses tissue without a splash or shock wave, and the relevant number is not simply how much radiation exists, but how it deposits energy in a body. Chapter 6. Acute ionizing radiation. Ionizing radiation carries enough energy to remove electrons from atoms and molecules. It can interact directly with DNA or create reactive chemical products from water and other molecules inside a cell. Cells possess repair systems, but a sufficiently large dose delivered quickly can overwhelm them across many tissues at once. Acute radiation syndrome is not the result of every exposure. According to clinical guidance from the United States Centers for Disease Control and Prevention, the dose must be high, penetrating, delivered to all or most of the body, and received over a short time. A small local exposure, a low dose spread over years, and a sudden whole-body exposure are not equivalent events. The gray measures absorbed energy per unit mass, 1 joule per kilogram. That physical definition is simple, but biological consequences are not. Radiation type changes how densely energy is deposited. Dose distribution changes which organs are affected. Dose rate gives repair processes more or less time. Age, health, and treatment change the outcome. The sievert is used for radiation protection quantities that weight radiation type and, in some contexts, tissue sensitivity. It should not be substituted casually for gray in a medical scenario. Saying that a person received a certain number of radiation units without defining what was measured can produce a false comparison. For an acute penetrating whole-body exposure, the CDC describes the full bone marrow syndrome as usually occurring from roughly 0.7 to 10 gray, with mild symptoms possible at lower doses around 0.3 gray. This is a broad clinical range, not one cliff. As dose rises, the probability and severity of illness rise. The first phase may include nausea, vomiting, loss of appetite, and fatigue. Timing varies with dose. A latent phase can follow in which the person appears or feels better even while stem cell populations are being lost. That temporary improvement is one of the most counterintuitive features of the syndrome. Bone marrow continually produces blood cells. Damage to its stem cells reduces white blood cells needed for immune defense, platelets needed for clotting, and red blood cells needed for oxygen transport. Infection and hemorrhage become major dangers. Medical care can include isolation, antimicrobial treatment, transfusion support, and drugs that stimulate blood cell recovery, depending on circumstances. The CDC gives an approximate LD50 over 60 days of about 2.5 to 5 gray for the reference exposure conditions. LD50 means a dose associated with death in half of an exposed population over a stated period. It is not a prediction for one named person. The range itself reflects biological variation and differences in care. At higher whole-body doses, gastrointestinal injury becomes dominant. The CDC describes the full gastrointestinal syndrome as usually occurring above about 10 gray, while some symptoms may appear around 6 gray. Rapidly renewing cells lining the digestive tract are lost, contributing to severe diarrhea, dehydration, electrolyte imbalance, infection, and profound marrow damage. At still higher doses, cardiovascular and central nervous system injury can develop. Full syndrome is described above roughly 50 gray, with some symptoms possible from around 20 gray. These figures apply to particular kinds of penetrating radiation and broad whole-body exposure. They must not be converted into a universal chart for every isotope, particle, accident, or medical treatment. Radiation is sometimes described as invisible fire, but even that metaphor can mislead. A thermal burn transfers heat. Ionizing radiation deposits energy through atomic interactions, and the biological injury may unfold after the exposure has ended. A detector may reveal the field immediately while symptoms emerge on a different schedule. Radiation protection also distinguishes deterministic tissue reactions from stochastic risk. Above certain dose ranges, the severity of tissue injury tends to increase with dose. Cancer risk is discussed probabilistically and can matter after much lower exposures over long periods. Acute radiation syndrome belongs to the first problem, a large short-term insult to whole-body systems. It should not be used to describe every medical scan, occupational exposure, or trace of natural background radiation. The hard lesson is that life depends on renewal. Blood, intestinal lining, skin, and many other tissues are maintained by cells dividing in carefully regulated cycles. Acute radiation injury can break that renewal system. The person may look intact while the capacity to replace essential cells is disappearing. From microscopic damage, we now turn to the largest object directly beneath us. Humanity has crossed hundreds of millions of kilometers through space, yet our deepest vertical borehole reached only a tiny fraction of Earth's radius. Chapter 7. The Deepest Hole. The Kola superdeep borehole reached 12,262 meters. That is more than 12 kilometers of drilled depth, a major engineering achievement. Earth's mean radius is approximately 6,371 kilometers. Divide the borehole depth by that radius and the result is about 0.192%. The comparison is almost unfair. A 12-kilometer hole is enormous on a human map and nearly invisible on a full Earth cross-section. It remained within continental crust. It did not reach the mantle, and it did not open a path toward Earth's core. Deep drilling is not simply surface drilling repeated more times. Every additional section of borehole adds a long mechanical and thermal system. Drill string, casing, fluid circulation, rock removal, measurements, and control signals must function through kilometers of changing conditions. The borehole itself can deform, deviate, fracture, and interact with fluids in the rock. Temperature was one major challenge at Kola. Measurements were hotter than early expectations, and rock behavior became increasingly difficult for the equipment and borehole stability. But saying the heat stopped the drill erases the combined engineering, material, operational, and historical constraints. Deep projects end because systems and institutions meet limits together. Pressure also changes with depth, but there is no single simple pressure equal to the weight of a neat vertical column. Rock supports stress in different directions. Pores may contain fluids. Temperature changes material properties. Fractures and tectonic history produce local conditions. Engineers measure and model the formation rather than extrapolating one surface equation to the center. If drilling continued, the crust would not suddenly turn into a global ocean of magma. Most of the mantle is solid on short human timescales. It can flow over geological time because hot rock deforms slowly under stress. Solid and flowing are not contradictions when the time interval changes by millions of years. The boundary between crust and mantle is identified mainly through seismic waves. Their speeds change as they travel through materials with different composition and physical state. Earthquakes provide signals that cross the planet, allowing scientists to infer layers no drill has sampled directly. Laboratory experiments then reproduce high pressures and temperatures on small samples. Gravity measurements, magnetic observations, heat flow, meteorites, volcanic rocks, and Earth's moment of inertia add independent evidence. None gives a photograph of the core. Together they constrain models of a silicate mantle, a liquid metallic outer core, and a solid inner core. Scientific confidence comes from agreement among methods with different weaknesses. An imaginary indestructible drill does not solve the full problem. Material removed from the cut must go somewhere. The hole must remain open. Heat must be transported. A power source and communication system must operate. Once a path reached material that behaves ductily on the relevant timescale, the walls would tend to close unless continuously supported. Even the word hole hides its geometry. A deep borehole is narrow, can deviate from vertical, and may include multiple branches or sections of casing. Its measured depth along the drilled path and its true vertical depth are not always identical. The Kola record is usually given as measured depth. Comparing that number with Earth's radius is a useful scale illustration, but it is not a claim that a perfectly straight open tunnel extends 12 kilometers downward. Going deeper also does not mean gravity simply becomes stronger all the way down. Inside a roughly spherical planet, only the mass at smaller radius contributes to the inward gravitational pull in the simple shell model, while outer shells cancel. Density changes complicate the curve, but at the exact center the pulls from all directions balance and local gravitational acceleration approaches zero. That does not make the center gentle. Pressure arises from the weight and compression of overlying material, and temperature remains extreme. Zero net direction of gravity at one mathematical point is not zero pressure or zero energy. It is another example of everyday words failing when scale and geometry change. Kola's value is not that it almost reached the core. It did not. Its value is that a direct measurement tested expectations and forced geologists and engineers to confront real rock instead of a clean diagram. The deepest hole is a monument to how science advances, not by conquering a planet in one gesture, but by making one narrow path of uncertainty smaller. The next impact comes from above rather than below. Because most of Earth is covered by ocean, a hazardous asteroid is more likely to encounter water than a city. But water does not guarantee either safety or a planet-wide wave. Chapter 8. An asteroid strikes the ocean. There is no single ocean asteroid. Outcomes depend on diameter, density, strength, speed, entry angle, water depth, seabed geology, distance to a coast, and the population in harm's way. A fragile object may fragment and release much of its energy in the atmosphere. A stronger or larger object may reach the surface. A near-coastal impact is a different hazard from one in the remote deep ocean. NASA's Asteroid Threat Assessment Project models this chain rather than assuming every object makes a crater. Entry heating, aerodynamic loading, breakup, airburst, surface impact, blast, thermal radiation, tsunami, and possible global effects are connected stages. Uncertainty in an asteroid's properties creates a range of possible outcomes, not one movie scene. Suppose our object survives to strike deep water. Its kinetic energy is transferred rapidly into water, vapor, air, the asteroid, and perhaps the seabed. A transient cavity forms. Water is accelerated outward and upward. Vapor and fragments enter the atmosphere. Gravity then drives water back toward the disturbed region, generating waves. Near the impact, conditions can be devastating. But a common assumption used to be that even a comparatively small asteroid in the ocean would generate an efficient, basin-crossing megatsunami. Later workshops and modern simulations found a more complicated picture, especially for objects below a few hundred meters. Earthquake tsunamis often begin when a broad area of seafloor displaces an enormous volume of water, creating very long wavelengths that travel efficiently across an ocean. An impact can deposit energy into a more compact region and produce a spectrum of shorter waves. Braking, turbulence, and dispersion can remove energy as those waves spread. This does not make the tsunami harmless. Flooding close to an impact can be extreme. Continental shelves, coastal shape, water depth, and impact location affect how energy reaches shore. A strike near a populated coast may create little warning time and serious inundation. The correction is about global efficiency, not the absence of local risk. We must also separate a wave's height in deep water from coastal run-up. As a tsunami approaches shallower water, its speed and shape change. Local topography can focus water into bays or allow it to spread. One global number cannot describe every coastline. A dramatic wall drawn at the same height around a world map is not a physical forecast. Blast and thermal effects may matter even when the impact point is water. An incoming body can produce a powerful atmospheric shock. Hot vapor and ejecta can radiate energy. Which hazard dominates depends on the scenario. For smaller stony objects, an airburst may be more probable than a clean seabed strike. For a much larger object, regional and global mechanisms become possible. Climate effects require special restraint. A sufficiently energetic impact can inject material high into the atmosphere, alter incoming sunlight, and disturb climate. But the amount and composition of that material depends strongly on the impact site and size. Vaporized seawater, salt, dust, sulfur-bearing rock, and soot from fires do not all produce the same effect or remain aloft for the same time. Chicxulub cannot be used as a generic ocean impact template. That event involved an enormous object and a particular shallow water geological target rich in materials that affected the atmosphere. Changing the asteroid or the target changes the outcome. Saying it hit water, therefore dinosaur extinction, skips the variables doing the actual work. Planetary defense therefore begins before consequences. Surveys search for near-Earth objects. Repeated observations refine an orbit. Spectra, radar, and brightness help estimate size and composition. If a threat is discovered early enough, changing its velocity by a tiny amount can make it miss Earth by a large distance years later. Risk combines consequence with probability. A rare large object can have enormous potential consequences, while smaller objects are encountered more often and may produce regional damage. Population distribution changes human risk even when the physics of the impact is the same. This is why threat assessment samples many possible objects, trajectories, and impact sites rather than publishing one dramatic animation as the expected future. The 2022 DART mission demonstrated that a spacecraft impact could measurably change the orbit of a small asteroid moon. It was not a complete defense system and the target was not heading toward Earth. It was an experiment showing that orbital momentum can be altered and measured. Deflection is attractive because it prevents every downstream hazard at once. An ocean is neither a shield nor a guaranteed global amplifier. It is a dynamic medium inside a larger coupled system. The scientifically useful question is not land or water, by itself. It is, what object, what trajectory, what water depth, what geology, and what distance from people. We have now watched matter move through air, water, rock, and an entire planet. The next boundary is not a material surface at all. It is a horizon, a place where the paths leading outward disappear. Chapter 9. Falling toward a black hole. A black hole is a region of spacetime from which future-directed paths cannot carry matter or light back to the external universe. The event horizon is the boundary of that region. It is not a solid shell and it is not necessarily marked by a local flash, wall, or alarm. Imagine a probe falling toward an isolated, non-rotating black hole while transmitting one pulse every second according to its own clock. A distant receiver does not continue to receive those pulses unchanged. The intervals between arrivals grow. The light is gravitationally redshifted to longer wavelengths and loses detectable intensity. Popular explanations say the observer watches the probe freeze forever on the horizon. That phrase captures part of a coordinate description, but it can create the wrong picture. A real telescope does not receive an eternally sharp frozen portrait. The signals become delayed, redder, and fainter until they are effectively undetectable. What the observer knows is limited by the light that can still escape. For the falling probe, its own clock behaves normally. Proper time is the time measured along its path. It reaches and crosses the event horizon in a finite amount of proper time. There is no local moment at which its electronics conclude that time has stopped. The disagreement is not a broken clock, it reflects different paths through curved spacetime and different definitions of simultaneity. Crossing safely is another question. Tidal force is the difference in gravity from one part of an object to another. Near a small stellar mass black hole, that gradient can become destructive outside or near the horizon. Near the horizon of a sufficiently supermassive black hole, the gradient can be much weaker because the horizon is much larger. That does not make a real galactic black hole a safe destination. Many are surrounded by accretion disks of extremely hot plasma, magnetic fields, and intense radiation. Our clean thought experiment removes that environment so we can isolate spacetime geometry. The absence of lethal tides at one boundary would not guarantee survival elsewhere on the trajectory. Inside the horizon, moving outward locally is still possible in the same sense that a person can fire a rocket in any local direction. The deeper global problem is that all future-directed routes remain within the black hole region. The geometry makes decreasing distance toward the interior as unavoidable as moving toward tomorrow is outside. General relativity predicts that continued collapse leads to singular behavior where curvature becomes unbounded in the classical theory. It is safer to treat that as a warning about the theory's domain than as a photographed object of literally infinite density. Quantum physics is expected to matter, but no experimentally confirmed theory yet gives a complete description of the interior. Rotation makes the mathematical structure more complicated. Astrophysical black holes are expected to spin. The ideal Kerr solution contains features absent from the simple non-rotating case, but extending its internal geometry all the way into a realistic, disturbed black hole raises difficult stability questions. Our documentary does not need to pretend those open problems are settled. Time dilation is not unique to black holes. Atomic clocks at different elevations on Earth tick at measurably different rates because gravitational potential differs. Satellite navigation systems account for relativistic effects. A black hole takes a real phenomenon already present near Earth and drives it toward an extreme. The equivalence principle gives a local reason gravity and acceleration are connected. Inside a sufficiently small freely falling laboratory, the occupants feel weightless even while the laboratory follows a curved path through spacetime. No local experiment in that tiny region labels one moment as crossing the horizon for a large quiet black hole. The horizon is defined globally by which light paths can escape to the distant future, not by a material detector buried in space. It is also important not to promise the falling traveler a view of the entire infinite future of the external universe. Signals from outside are affected by the trajectory, the black hole, and the limited proper time remaining. Some outside events may appear accelerated or distorted, but watch all eternity before crossing is not a general conclusion. The event horizon teaches a deeper lesson about observation. What exists locally, what a distant observer can receive, and what a coordinate system assigns to an event are related but not identical statements. Confusing them produces the famous frozen astronaut. Separating them produces a stranger and more accurate picture: the astronaut crosses, while the final information about that crossing cannot return. One black hole hides a region behind an event horizon. Cosmology gives us horizons on a vastly larger scale, produced not by one collapsed object but by the history and expansion of the universe itself. Chapter 10. Why even light speed is not enough. The universe is about 13.8 billion years old, yet the observable universe is approximately 92 billion light-years across. That is not a contradiction. The light we receive from the most distant regions traveled while space itself was expanding. Their present distance is much greater than light travel time multiplied by c in a static universe. The phrase, observable universe, names a limit on information, not a physical wall. We occupy the center of our observable region because observation looks backward along light paths reaching us now. An observer in a distant galaxy would occupy the center of a different observable region. Neither location is established as the center of the entire universe. Several different cosmic scales are often given the same name, which causes confusion. The particle horizon is connected to the farthest region from which light has had time to reach us since the early universe. The Hubble radius is c divided by the Hubble parameter at a given cosmic time. The cosmological event horizon concerns signals emitted now that can ever reach us in the future if the expansion follows a given history. These boundaries are not generally identical. Crossing the Hubble radius does not automatically mean a galaxy disappears forever. A galaxy can recede from us faster than c because cosmological recession is not ordinary local motion through one inertial frame. Light it emitted in the past may still reach us as the expansion rate changes along the journey. This corrects a popular but misleading river analogy. It is tempting to say that beyond one distant space flows outward faster than light can swim toward us. The analogy can help, but it hides the time dependence of the expansion. Whether a photon reaches us depends on the entire evolution of the scale factor, not only on one recession speed measured at emission. Locally, every freely moving observer still measures nearby light traveling at c. General relativity does not allow a rocket to pass a local light beam by accelerating through space. The expansion of distance between far-separated, comoving galaxies is a different geometric statement. It can produce recession rates greater than c without providing a local faster-than-light engine. Cosmological redshift records that expansion. As a light wave travels through expanding space, its wavelength is stretched. Distant galaxies therefore appear at wavelengths longer than those at which the light was emitted. Telescopes observe different portions of the spectrum to recover information shifted out of visible light. Accelerated expansion gives the event horizon question its force. In the standard cosmological model, there are sufficiently distant regions from which a signal emitted today will never reach us, even given unlimited future time. The boundary depends on the future behavior of expansion, which is inferred from a model and observations. It is not painted on the sky. There are also galaxies we see today whose current events can never become visible to us. The photons in our telescope left them long ago, when the relevant causal relationship was different. We see their history, not their present. Astronomy is always an archaeology of arriving light. Distance in cosmology must therefore be labeled. Look-back time describes how long the detected light traveled. Proper distance refers to separation measured on a chosen cosmic time slice. Commuting distance factors out the overall expansion to track objects carried with the cosmic flow. A galaxy can have a look-back time near the age of the universe while its present proper distance is much larger than that number in light years. Mixing these distances creates many apparent paradoxes. No spacecraft can solve this by simply reaching c. An object with rest mass cannot reach light speed because the required energy grows without bound. At any sublight speed, travel across cosmic distances consumes time in some frame, and expansion continues. Relativistic time dilation can reduce the traveler's elapsed time for a sufficiently fast journey, but it does not create a return path from beyond a true event horizon. The actual universe may be much larger than the observable region. It may be spatially infinite. Current science has no reliable measurement of its total size. Statements about the size of the universe should therefore specify whether they mean the observable universe or the unknown whole. This final scenario reverses the scale of the first. A relativistic marble revealed that approaching c can store immense energy in a tiny object. The cosmic horizon reveals that c, despite being the fastest local carrier of information, does not make every region mutually accessible in an expanding spacetime. We began with the question of what happens when a rule is broken. We end with a boundary that requires no broken rule at all. Light moves exactly as fast as nature permits, and some information still cannot arrive. Conclusion. 10 scenarios have taken us from 5 grams of glass to the observable cosmos. The most spectacular image was rarely the most accurate explanation. The relativistic marble did not remain a marble until it made a neat crater. Water did not become concrete. A person in vacuum did not explode. An astronaut did not feel their own clock stop at a black hole horizon. In every chapter, the answer depended on defining the problem. Where did the marble deposit its energy? Which parts of Earth were stopped, and by what torque? What kind of radiation, delivered where and how quickly? What asteroid, at what angle, into which ocean depth and geology? An omitted assumption can change a result more than another decimal place ever could. Physics is powerful because it limits claims as well as enabling them. Relativity calculated the marble's kinetic energy. It did not supply an unsupported damage radius. Clinical evidence described radiation syndromes as ranges. It did not predict one person's fate from one number. Cosmology described horizons, but it did not reveal what lies beyond everything we can observe. This is not a weakness in science. It is the difference between a model and a myth. A myth gives one vivid answer immediately. A model states its assumptions, predicts what follows, and shows where more evidence or computation is required. The universe we inhabit is extreme even when nothing impossible happens. Earth really rotates at hundreds of meters per second near the equator. Gravity really communicates changes no faster than light. Atomic clocks really disagree when they follow different paths through spacetime. Particles from space really create showers in the atmosphere. Our survival is not proof that nature is gentle. It is evidence that life evolved inside a narrow, persistent set of conditions: atmospheric pressure, liquid water, manageable radiation, a stable orbit, and an energy source arriving from one star. Move far outside those conditions and familiar intuition loses its training data. Thought experiments let us travel there without pretending to have witnessed the event. Their purpose is not to make catastrophe look inevitable. Their purpose is to reveal which principle carries the explanation: conservation, causality, momentum, pressure, energy deposition, material behavior, or geometry. They also train a habit useful far beyond physics. Ask what was measured. Ask which quantity was calculated. Ask whether a comparison shares only an energy scale or the same mechanism. Ask what changes when an assumption changes. A dramatic claim becomes more interesting, not less, when its uncertainty is visible, because the viewer can finally see the boundary between evidence and invention. At the hard ceiling of any question, the most scientific words may be these: this part is known, this part is calculated, this part depends on the assumptions, and this part remains unknown.